Okay, so we're back to first derivative test stuff, get a little more practice on that. So finding extrema with using the tables. So let's try another one. Let's try a trig function this time. So quick review, right? Somebody want to articulate what our strategy is here? How do we use these tables to find extrema? And in the process of doing that, kind of a fringe benefit is we're also able to define all of the increasing and decreasing intervals. So how do we do that? What's our strategy? Some brave soul?
Find critical points.
Okay, so we're going to find all the critical numbers. Find the values of x where the derivative is undefined or equal to 0, right? And then to determine, how do we use the first derivative test? To determine if those are extrema, how do we use the first derivative test? Okay, that's where that's equal to 0 or undefined. Let me turn you. Boy, yours is quiet, Emma. Let me say that. I'm gonna turn up the volume. Say that again. I didn't catch everything. Okay, those are the critical numbers, but how do we determine using the first derivative test whether or not those critical numbers correspond to extrema? Because they might be, or they might not be. They might be false alarms.
Do you find if the slope is negative or positive?
Yeah, we're going to pick with test points, right? We'll pick test values immediately to the left or the right of the critical numbers, right? And we'll by evaluating the sign of the derivative at those test points, we can determine whether or not the function has a maximum or a minimum at each of the critical numbers. Okay. So to do this, we need the first derivative though, right? So let's go ahead and calculate our first derivative for this function. What is our first derivative? Now you got to be careful. This sine squared x, remember that's shorthand for the quantity sine x squared. So what is f prime of x there? What's f prime? Natalie, what's our first derivative going to be there?
Is it 2 negative cosine?
Okay, the derivative of sine is positive cosine, right? But I'm still missing something there, right? The sine squared x, remember, sine squared x equals the quantity sine x squared. How many links do I expect in my chain there, Natalie?
There's 2.
There's got to be 2. Okay, so what's the first link going to be?
Is it 2 sine x, so like hand?
There you go, good. So 2 times, we've got the derivative of hand squared is 2 times hand to the 1, right? So 2 sine x times the derivative of what's inside. Now I've taken care of the power function. Now I look inside that. What's the derivative of sine?
So then it's cosine.
There you go. Okay, everybody see that? So that's my derivative. I've got to have 2 links in the chain, and there's the product. There's the multiplication sign between the 2 links in my chain, right? Let me make this, just to make this more obvious, I want to highlight that point. How about if we do it this way? 2 sine x cosine x. So the derivative of the second link is in red. Okay, plus, keep going. Natalie, what's the second term in my derivative? The derivative of sine is just
cosine.
There we go. Cosine x. So there's my derivative function, okay? We need to find critical numbers. So we got to ask the question, is this undefined anywhere, and where is it equal to 0? Well, let's deal with the undefined part first. Is this function undefined anywhere? Yes or no, and why? How come, Seth? You're right.
Well, I mean, there's nothing in here that could go undefined. There's nothing on the, there is no bottom. The bottom is one. And then you can put any value sine x, cosine x, and go up to that constant. So nothing here can be undefined.
Okay, yeah, why would this be undefined? There's no reason it would be, right? Sine and cosine individually, neither of those are undefined anywhere. Sine is just it's just a wave, a sinusoidal function that just, it goes forever to the left and the right. Same with cosine. They're just offset a little bit, right? Really, sine and cosine are the same function, just phase shifted a little bit. So there's nothing I can't input there, nothing I can't input there, and nothing I can't input there. So why would a product be a problem? Well, it wouldn't, right? If sine's okay everywhere and cosine's okay everywhere, so's the product of those two. And then adding another cosine wouldn't change that either, right? There's no red flags that pop up in any of these functions. There's no place where we would be asked to divide by 0 or take an even root of a negative number or anything like that, right? So our domain is all real numbers, and we're going to limit ourselves a little bit. Here, we're only looking on a certain portion of the domain. But on our domain, this is nowhere, the derivative is nowhere undefined. So let's make a note of that. Okay, so what about where this equals 0? What could I do with my derivative here that might be useful? If I'm trying to find the zeros of this, what do we always really want to try to do when we're finding zeros? Suggestions? Yeah, we want to factor, don't we? What could we factor out, Kirsten?
The cosine x.
Yeah, good. We could factor out a cosine. Good job. So we end up with cosine x times, we'd end up with a 2 sine x plus 1, right? And I've got this thing factored now by the zero product property. F prime equals 0 when one of two things happens. Either when cosine x equals 0 or 2 sine x plus 1 equals 0. Well, if I solve that for sine x, isn't that the same thing as saying when sine x equals negative 1/2? Anybody agree? Okay, so look, our domain is just one lap of the unit circle, isn't it? Right? But we're not including 0 or 2 pi. So let's take a look here at, oops. Okay, so let's, oh, you know what I want to do? Here, I want to do one thing real quick. Okay, this is going to take just a second to do. So what do we want to talk about for 15 seconds? Anything important? No ideas? How about that?
Astrology, Mr. Mayor.
On astrology? What do you think my thoughts are on astrology, Johan?
I just want to hear what you have to say.
Okay, on a scale of 0 to 100, 100 meaning I think that it informs a lot of our decisions. It's reasonable, and 0 meaning it's absolutely worth nothing. I'm going to say 0. Yeah. Okay, so there, it worked. Okay, so unit circle And I got to think, what were our two? Here, let me grab a picture of this. Oops, that didn't work. Okay, so those are our two conditions, right, for zero derivative. So let's look on our unit circle where that's going to happen. Can you guys draw straight lines like that? I bet you can't. So I was cheating. So where is cosine equal to 0 on the unit circle? Now, cosine is the x coordinate, right? Right, c before s, x before y. So, okay, see, people are pointing up to the top. There you go. So one place where it's equal to 0 is there, right? So this happens there and there, doesn't it? And on the unit circle, those are going to be at the angles pi halves and 3/2 pi. Okay, what about this? Where is sine x equal to negative 1/2? Where is the y coordinate equal to negative 1/2? Well, negative 1/2, that's negative 1. So negative 1/2 is going to be right there, positive, right? Those two places, right? At this point and at that point. So those are going to be the places on the unit circle where the y coordinate is negative 1/2. What angles are those? Think in the first quadrant where that happens. In the first quadrant, we've only got a few important places, right? We've got a point there, we've got a point there, and we've got a point there. Those are my interior values in the first quadrant. This is the one that has coordinates where x is big and y is small. This is the one where they're equal. And this is the one where x is small and y is big. I showed you guys the finger trick, right? For quadrant 1. Did I show that to you? Oh gosh, I got to show you the finger trick. I didn't show you that for the unit circle? Oh my goodness. Okay, I got to show that to you. Okay, so can you see me now? Okay, so here's what you do. This is going to be a little backwards. So you put your hand up, right? And you're going to count. So this is in quadrant 1. This my pinky is going to be the x axis and my thumb is going to be the y axis, right? And I've got these 3 interior angles there, okay? If we're at 0, which is on my pinky, then the x coordinate is always going to be the square root of the number of fingers above, can't wiggle my pinky, above that pinky, right? So the square root of 4 is 2, right? 2 divided by 2. I'm always going to divide the square root of whatever the number of fingers are by 2. So the square root of 4 over 2 is 1. So my x coordinate is 1 there, right? How many fingers are there below my pinky? 0. So the y coordinate is 0. If I scoot up to, now that's really hard. If I scoot up to the next finger, right, that's the first angle. Okay, that's going to be the one that's 30 degrees or pi 6, right? So the x coordinate is going to be the square root of 3. I've got 3 fingers above that one, right? So the square root of 3 over 2. The y coordinate is the square root of 1, which is 1 over 2. Isn't that cool? If I go up to the next one, right, the next one is going to be the 45 or the pi fourths. The x coordinate is the square root of 2 over 2. The y coordinate is the square root of 2 over 2. If I go up to this one, right, that's going to be 60 degrees or pi thirds. X coordinate is the square root of 1, which is 1 over 2. Y coordinate is the square root of 3 over 2, right? And then finally, if I go up to my thumb, the x coordinate, there's nothing to this side of my thumb, above my thumb, right? And so I get 0 is the x coordinate, and the square root of 4 is 2 over 2. 1 is my y coordinate. Isn't that cool? Great way to remember it. Okay, there's my little hand trick. Okay, back to business. So then this is going to be, this angle right here is pi 6, right? Pi 6 radians. So if that's pi 6 radians, then this one right here must be 2 pi minus pi 6, right? So that's got to be 11 6 pi. And this one right here has got to be pi halves plus an extra pi 6. So that's going to be 7 6 pi. Okay, everybody see that? So those are my critical numbers, aren't they? Those are the values of the angle x that are going to make these two conditions true. And those are the conditions where my derivative equals 0, right? So we can go back to our table here, and we can add those values, right? So we're going, let's first of all add our domain on our table. So we're going all the way from x equals, we wouldn't actually add 0, but values greater than 0 and less than 2 pi. And the angles we had were pi halves, 7 6 pi, 3 halves pi, and 11 6 pi. So we got to add those to our table. Okay, so pi halves is right here. I'm going to scoot this over a little bit this way to give myself more room. So pi halves, we had 3 halves pi. And then we had the critical numbers, what was it, 7 6 pi? This isn't quite to scale. And 11 6 pi. And those are all places where our first derivative was equal to 0, right? And so we know those are going to be places where we have horizontal tangents. So there's our icon for horizontal tangents. Now what? Those are my critical numbers. Now what do I do?
Plug in the critical numbers into the original function.
I can, yeah. If I want to find the y values, absolutely, I can do that. Okay, so let's do that. I'm going to cheat here a little bit and use Desmos for that. How about? You don't mind, I bet, huh? So there's the original function. Let me type this in real quick. Okay. Oh, where'd it go? Did I delete it? That was kind of dumb. Okay, I gotta go. Gotta enter it again. What would happen if I do sine squared x? Does it know what to do? Oh yeah, it does. That's good. All right. Okay, that was my original function, right? Yeah. Okay. So let's evaluate that. Oh, I got to be in radians. I'm in radians, good. So let's evaluate that at pi halves. I get 2. Okay. If I evaluate that at 3 halves pi, get 0. Okay, I'll just put all these on here at once. Oops. Okay. Negative 1/4 and f of negative 1/4 for both of those. Okay. Okay, so those are my values. Okay, that's nice to know, but I don't know if those are extrema yet, right? Where'd you go? There we go. So now what? How do I determine if those are extrema? Got to use the first derivative test, right? So what's the first derivative test?
Find the derivatives on either side, both values.
Okay, I got to pick test values, right? I don't need to find the derivatives. I just need to find the signs of the derivatives. I can make this easier. So I've got all these points. Let's pick some test values here. So what do you say for our test values? We could go like pi fourths. Here, this is going to be kind of a tougher one, right? Here, we're going to have to do something like, there's really no convenient value between pi halves and 7/6 pi. So we'll do something like 15/12 pi, or hold on, what's that going to be? 15. No, that's the wrong way. So like 13/12 pi, right? That's not a very convenient one, is it? And then between 7/6 pi and 3 halves pi, we could do 5/4 pi. And then here we could do 7/4 pi. And what about here? I could pick a test value in between 11/6 pi and 2 pi, but in this case, my function is continuous everywhere. I'm imposing this domain on it, right? Everybody agree? Because the function does exist mathematically at that endpoint, I could just use the endpoint and take a limit. Okay, how about if we just did that instead? What if we took a limit here at the endpoint? So I guess I want to make that green. We'll take a limit as x approaches 2 pi. That should be easy to evaluate, right? Okay, so what are I've got this thing factored up here, don't I? I've got it factored into cosine times 2 sine x plus 1. At pi fourths, we ought to be able to figure this out. What are we going to get at pi fourths? We're going to get quadrant 1, that's positive. That's going to be positive too, isn't it? I get positive times positive at pi fourths, so I'm getting a positive first derivative. Okay, what about just a smidge past pi halves? What's going to happen there? What's the sign of this going to be? So the cosine is going to be negative, isn't it? Because that's going to be almost, I mean, it's going to be just barely into quadrant 3. Cosine is negative every place in quadrant 3, right? So we're going to get a negative times, what about this? 2 times the sine that's going to be a really small negative value, isn't it? Everybody agree? Looking on the unit circle, I mean, we're going to be up here somewhere, right? That's a pretty small, everybody agree that's a small negative sign value? It's going to be a number whose absolute value is less than 1/2, right? Something, close to -1/4, plus or minus a little bit. Whoops. And so we can tell what that's going to be. I'm going to end up with a negative value here that is less than 1 plus 1 makes that positive, right? Now I could plug it in and actually evaluate the function and figure out what the actual value of the function is, but I don't want to. We don't need to, right? All we need is the sign, and it's clearly going to be a negative. Negative times positive is negative. Okay. What about at 5/4 pi? That's right in the middle of quadrant 3. So I'm going to get negative. Here I'm going to get 2 times square root of 2 over 2, negative the square root of 2 over 2. That is bigger than negative. What's that going to be? Square root of 2 over 2. Yeah, that's going to end up being a negative number. 2 times that negative value is going to be a negative number bigger than -1. I'm going to get a number that's more negative than -1 plus 1 is going to give me negative times negative, isn't it? You get negative times, that's going to be a negative factor. If I plug in negative the square root of 2 over 2 right there, I'm going to get a negative value. So negative times negative is positive. And then at 7/4 pi, I'm right in the middle of quadrant 4. So that's going to be positive, right? X is positive there. And this factor is going to have the same value it did at 5/4 pi, which is going to be negative. And so I end up with a negative result. And then what about at 2 pi? If we take a limit at 2 pi, what are we going to get? As x approaches 2 pi, the cosine is approaching 1, right? Positive 1. And the sine is approaching 0, right? 2 times a number that's approaching 0 is really small, plus 1 looks a lot like 1, doesn't it? So positive 1 times positive 1 is definitely positive. Okay, so then what's that tell me? What have I got here? If it's a transition from a positive increasing first derivative to a decreasing, what's that look like? What kind of animal is that? Kyle, what is that?
Is it an extrema?
Which kind? Max or min? Increasing, transitioning to decreasing. It's a maximum, isn't it? Good. So we're going increasing to decreasing. So that's a max. Here we go decreasing to increasing. So that's a min. Increasing to decreasing, that's a max. Decreasing to increasing, that's a min. Okay. So we found them all. And then the periods where it's increasing, well, increasing is going to be any interval where it's got a positive first derivative. So it's positive from 0 to pi halves. It's positive when x is greater than 7/6 pi and less than 3/2 pi on that interval. And then it's positive when x is greater than 11/6 pi and less than 2 pi, right? And then decreasing would be all the negative intervals, okay? Give me 1 to 5 on that. Does that make sense? Okay, let me take a picture of that and we'll look at the actual graph and just compare it to the actual graph. Okay, so if I graph that in Desmos, oh, I already did it, didn't I? It's down here. Okay, there's my graph. Okay, there it is. That makes sense. Doesn't that fit our wait, 3 halves? We had one at oh, did we miss a couple here? 7/6 pi. What the heck? How did we miss one? Sin x equals -1/2. Oh, no wonder. Yeah, we only went from 0, didn't we? Whoops. So ours just does this. See, I know we did that right. Right, ours is just doing this. So look, we got extrema at, there's our pi halves, there's 3 halves. There's our 7/6 pi, there's our 11/6. Okay, got it right. Okay, questions? Okay, let's try another one. We just got to get practice in on these. So let's do a little bit of an applied one here. So electric power P in watts in a direct current circuit with 2 resistors, R1 and R2, connected in series is given by this function, okay? Where V is the voltage and R1 and R2 gives us the resistance of the 2 resistors. Okay, if the voltage and R1 are held constant, what resistance R2 produces maximum power? So say that for some reason in this application, we have the ability to vary the resistance on R2, and we're going to try to pick a resistor that's going to maximize the power output of whatever this is. Who knows what this is, right? Some kind of a component that we're wiring up. What are we going to do? What are we going to do here? It seems really complicated because look, there's all kinds of V's and R1s and R2s and P. It looks terrible. But what's the only input variable here? What's the only independent variable? R2. The other stuff is just constant, right? So when we differentiate, that makes things a little easier, doesn't it? Right? So this is, let me write the variables in yellow, right? So that's a variable, and that's a variable, and all the other stuff is constant. And then P is our output variable, right? That's the function. Okay, so we want to differentiate this thing, right? Let's go to the next page and do that. Let's do our derivative first. Okay, so this is really P of R, right? And we're going to calculate the derivative P prime of R2. It's P of R2. That's what we've got to calculate here. So let's go ahead and just use quotient rule here. So help me out with this, right? Low D high minus high D low on this one. Madeline, talk me through this derivative here.
I don't really know. The variables are kind of confusing.
Okay, so remember, V and R1 are constant. The only variable here, think of it like an X, is R2. These other ones are just like we treat those just like any variable, like a pi or a number or anything. Those are, any constants. The V and the R1, those are constants, so their derivatives are 0, right?
Okay.
Okay.
So the first one would just be 0.
Right, but we're going to have to use the quotient rule, right?
Okay.
So we got low.
Okay, so that would be like 2. Oh, just the regular. Okay.
Right, we got low D high. What's the derivative of the top with respect to R2?
Wouldn't it just be 0?
No, answer me this. What's the derivative with respect to X of 3X?
Isn't it just 3x?
Yeah, it would just be 3, right?
Okay, yeah.
Right? So what's the derivative of VR1, R2 with respect to R2?
VR1.
There you go, right? It's this constant VR1 times the derivative of my variable, which is just 1, right? Derivative of R2 with respect to R2 would just be a 1. So I'm going to get VR1 minus the top, right? So VR1 R2 times the derivative of the bottom. Now that's going to have 2 links in the chain, isn't it? Because I've got a power function, and then inside that I've got something inside the power function. So what's that going to look like? What's the derivative of the bottom?
So it'd be 2 times, and then just the R1 plus R2.
Good. To the 1, right? Times.
Wouldn't it just be R1?
Well, now we're taking the derivative of what's inside. What's the derivative of R1?
R1?
R1's a constant. What's the derivative of R1?
Oh, so 0.
0 plus the derivative of R2 would be?
Just R2?
The derivative of R2, but we're differentiating with respect to R2. So that, so it'd be 1, wouldn't it? Good. So times 1. Just like if I were, everybody see that'd be like if I had something like the derivative of 3 plus x on the bottom, wouldn't I just get a 1 out of that if I'm differentiating with respect to x, right? So there's the top, and then divided by the bottom squared, right? So R1 plus R2 squared. Okay, let's simplify this. So we could factor out, we've got some like bases, don't we? We could factor out what's that?
Does the bottom need to be squared again?
Oh yeah, it should be a fourth, shouldn't it? Whoops, you're right. We squared the bottom, so squared is fourth, okay? On the top, we could factor out this like base, R1 plus R2, and then we could also, it looks like, factor out a VR1, the constants. So that's going to give us VR1 times R1 plus R2 times what's left over. So up here, I factored away the V and the R1, and I factored away one of those factors. So I'm left with R1 plus R2 minus minus, what about over here? Well, I factored that away. I factored that away. I factored that away. So I've just got a 2R2. It's all that's left over. All divided by R1 plus R2 to the fourth. So I could simplify that quotient, right? That just becomes a 3 on the bottom. And so we end up then with power P prime of R2 equals, what do I get here? So I'm going to get V R1 R1 plus R2 minus 2R2 is just R1 minus R2 divided by R1 plus R2 cubed. Okay? That was, I mean, really not so bad, right? We got all those constants in there that make that an easier derivative than it looked like it was going to be. So let's evaluate this thing. Now we've got our derivative function. Where is our derivative undefined? Where would it be undefined? How do we handle it? We got a rational function there. Where is a rational function undefined? What do you think? Where is a rational function, meaning a fractional function, undefined, Daisy? What would have to happen to make that undefined?
The bottom would have to equal 0.
Yeah, the bottom would be 0. Well, that would only, so R2 is the variable. That would be when R2 equals negative R1. Is that possible? You guys probably don't know much about electronics, but can I have a negative resistance? No. I tell you what, if any of you figure out how to generate a negative resistance, tell me first, and I'll go into business with you. Okay. That would be nice to, if you get that figured out, like I say, let me know. But it's impossible. So P prime is undefined nowhere. So we got no critical numbers from that. Where is it equal to 0? What's going to be the value of R2 that's going to make the top 0? Lily, what's going to be the value of R2 that's going to make the top 0? Wouldn't it equal 0 when this is the only factor in the top when that factor is 0?
Is it just that then? Or
Right. So when would that be 0? When would R1 minus R2 equals 0? Remember, R2 is the variable. R1 that's a constant, right? That's set in stone. What value would R2 have to have for that difference to equal 0?
would it have to be a value of R1?
It'd be the value R1, wouldn't it? If I solve for R2, I would just get the answer R2 equals R1, wouldn't I? So we maximize power when the two resistors are matched, when they have the same resistance, in other words, what we found, right? Okay, everybody see that? And we could go back, like if we wanted to make our table out of this, so I want to probably grab a picture of the derivative. Right? And if we go down to our table then, so for our table, how much time I got? I'm gonna have to hustle. For our table, our input was R2 instead of X. We were calculating power and P prime. Okay, in our domain, well, I didn't do our domain here. I should have done our domain at the beginning. Now, what's the logical domain for this? If R2 is a value of resistance, what's the lowest value of resistance that we could have? 0. Yeah. So we're going from 0 up to, well, we don't know what the upper limit is. We'll just call it infinity, right? So there's our domain. And we only got one critical number. And that critical number was when R2 equaled R1. And that gave us a 0 of the first derivative. So we know we have a horizontal tangent. So we just want to pick some test points. What if we pick test points like R1 over 2? And how about something like 2 times R1? And I just want to know what's the sign of my first derivative at those places. Well, look at this. We've got this thing factored. So what is P prime of R1 over 2? What's that going to give us? On the top, that's going to give us R1 minus 1/2 R1 is positive, isn't it? So I'm getting positive on the top. On the bottom, I'm always getting something positive because both the resistances are positive. Cubed makes it positive. So I'm getting a positive first derivative. What about at 2R1? So I'm going to get, positive constant times R1 minus 2R1 is going to give me negative R1 on the top. So I'm getting negative over my positive denominator. That's an overall negative sign. And so look what we get. That's our maximum for power. Pretty amazing, huh? Okay, give me a 1 to 5 on that. It was weird. The variables were weird. But once we kind of wrapped our brain around the fact that V and R1 are constant, R2 was the variable, just kind of an inconvenient variable. Not so bad. Okay, maybe we got 2 minutes, is that right? Yeah. The following figure gives the graph of the derivative of a continuous function f that passes through the origin. Sketch the graph of the function on the same set of axes. So wrap your brain around this. This is a graph of the derivative, right? It's a graph of the derivative. So let me write that down here. So this is f prime. Whoops. So look here. There's where the derivative has a value of 0, and there's where the derivative has a value of 0, right? So those must be horizontal tangent lines. Everybody see that? To the left of this 0, it looks like over here the derivative is negative valued because we're graphing the derivative function. Everybody see that? So over here it's negative. In here it's positive. And over here the derivative is negative again. So what could our function look like then? Well, it's going to have a horizontal tangent there, doesn't it? And it's going from a negative to a positive derivative. So that's going to have to be something like, well, here, let's do it this way. I'll put it down here. There's my horizontal tangent. Negative to positive means it's doing something like that, right? What about over here? Now I've got a 0 derivative again, so I've got a horizontal tangent. It's going from positive values of the derivative to negative values. So isn't it just doing something like that? Everybody see that? Okay, we'll practice some more. That's kind of the next thing I want to look at is just have you guys kind of think about conceptually about how do we relate this concept of derivatives and critical numbers to graphs. Okay, so that's what we'll do next time. This should get you going through most of the important parts of the assignment you can do now, especially the last problems that are the table problems. So get going on those. I'll extend the deadline a little bit so we can talk more about this, but we'll finish this up and start the next topic on Friday. There's a slight chance I won't be able to be here physically on Friday, so I may just have a pre-recorded lesson for you, okay? All right, have a good day. I'm here after school if you need me. Otherwise, I'll see you live or virtually on Friday.